I'm Joshua Heron. I'm a software architect at Autodesk working on Tinkercad. I'm very privileged to do so. It's a very small team and it's education focused, and I'm going to talk about what we've done to add robotics to Tinkercad. So let's see. So the agenda for today, what is Tinkercad? I'll give you a quick overview of that. Approaching robotics, how do we go about doing that? The implementation, incorporating Blockly, and then I'll give you some demos. And there will be some little demos along the way too. So what is Tinkercad? Well, I apologize, I'm going to read from the screen here because it'll be a lot easier. But so Tinkercad is a creative platform that combines 3D design, computational modeling, electronics design and simulation, and fabrication workflows into an accessible ecosystem for learning, prototyping, and making. It is free. There is absolutely no way to spend money on Tinkercad, which I love. It's beginner-friendly, browser-based. We have over 100 million users have chosen to use Tinkercad. We have more than 4 million teachers, and it's used in classrooms worldwide, and we support 15 languages. So Tinkercad is built up internally of 3 different editors. The first one is a 3D design, which is where Tinkercad started. Very simple, taking primitives out and adding and subtracting them to make something more complex. In the last few years, we also added physics simulation to that. So you can take whatever it is that you design and then apply gravity and collisions and see what that does. Then we also have code blocks. This is, centers around Blockly, and this is for designing your 3D models parametrically. So using your block coding to do that. And finally, we have circuits, which is an electrically accurate circuit simulator where you can just pull in discrete components, wire them up, and see what they do. And one of the really cool things about this, and I like to talk about accessibility, another aspect of accessibility, which is economic or what have you, where not everybody can afford to, a lot of classrooms can't afford to have the electronics. So here you can just go here and use as many parts as you want, break them if you want, and there's no consequence. And then this also has, we simulate both microbit and Arduino in the browser, and with both block and text coding. So approaching robotics. Let's see, we've been thinking about incorporating robotics. Once we added physics and we already have our circuit simulator, we thought, well, if we combine these two, does that get us to robotics? And well, there's some aspects about that. One is we're a really small team, even though we're inside of a larger organization like Autodesk. We are a team of, I think, 3 full-time developers that are working on the editor portions of this. And in fact, the entire simulation team is on stage right now. And both of these simulators are computationally expensive, even though they've been designed to work on low-end devices like Chromebooks and so forth. You take one really optimized simulation environment and another one, you add them together, and it may not work as well as you think it might. And that's been my fear. So it might not be performant. Also, by introducing the electronics and making that a necessary part to get to robotics, it's maybe too complex for a younger audience. And also, it's overkill for our goals. So no, this is not how you get there. Our general philosophies at Tinkercad are ease of use and accessibility to all ages. We kind of have in mind, kind of middle school as the middle of our target demographic. So we decided instead to just work with our physics engine and build a lightweight robotics add-on to that. So, and also to employ generic concepts like controller and motor and sensor of type whatever, instead of saying this particular piece of hardware. And that makes it so that we don't have to have users know a specific piece of hardware, just a general concept. And also, this gives us a future path if we want to go to a more technical offering of starting in robotics and then producing, say, a circuit that is equivalent to the hardware that you've designed, and in circuits or in a professional product like Fusion. So we've been thinking about this for a long time, about how to incorporate robotics into our product. And we've been taking some small but impactful steps along the way. Each of these is a feature in and of itself, standalone, but really gets us to the point that robotics can work. We've added in connectors and motors, so not just things falling down because of gravity, or we have you can throw things at things. If you want to introduce forces, you can actually just click and like throw random objects. But actually adding in motors to drive things and defining how they relate to multiple objects. And then key bindings, which give you keyboard control to drive motors. So you can say, set the speed or disengage the motor and that kind of thing. And then bundles, which allow you to group shapes together so that they are treated as a single shape as far as editing goes. So you can just click on it and drag the entire thing. But when you get to simulation, it simulates as separate objects. So implementation. First, coming up with an API. I'm just going to skip that because we don't care. Then had to develop a controller runtime. So this is, what is that lightweight engine doing to handle robotics? And so I developed a preemptive cooperative multitasking runtime environment using JavaScript generator functions and yielding to allow a robotics controller to run any number of handlers in parallel on a single JavaScript thread. So here's an example of how this runtime works. You can have any number of handlers, and those can be things like on start or a forever loop or on key press, on key release, that kind of thing. And here I've got two active handlers, which are the two lighter ones, and then an inactive handler over the side. And active handlers are just run in a round-robin fashion. So it does a certain amount of task on one and then switches to the next one and then keeps going back and forth. Each active handler periodically yields to the next handler. And events like key presses can activate inactive handlers. And then as a handler if it completes its final task, it then just goes inactive and can be activated again by events. Great. So then next steps were to develop an instruction set using an intermediate representation for use with robotics that includes all of the expected block types and maps to that API that I skipped over earlier. And then to assign a cost to each of those actions. So things like loops are costly because we don't want them to lock up the system. So every time you complete a loop, it eats a certain amount of virtual CPU, that kind of thing, or any tasks that may actually use a lot of CPU, we just assign them a cost. And then we took care to avoid blocking by handling loops and procedure nesting without blocking the system or locking up. Because again, this is all running on a single JavaScript thread that's pretending to be a multi-threaded environment and at the same time is simulating physics. Yay, nice. So what you would be seeing here if there were, oh, there it is, there's the video. So this is my proof of concept. We took our key bindings and just created a default robotics controller that takes those key bindings and implements them just as they were before, but instead using this robotics engine. So now incorporating Blockly. We've got everything working at this point. Now let's put an interface on this. So just a real quick thing. I mentioned we've got these three editors, the 3D and SimLab. SimLab, by the way, is the name of our physics. Code blocks and circuits. Code blocks and circuits already use Blockly in the form of Scratch. And so here we're adding Blockly as Blockly into our 3D editor, and I think it's just nice that we've got them on all of our editors now. Discussing incorporating Blockly. In general, Blockly was, already knew this was going to be the case, super easy to develop from the ground up, a new product. And these were the plugins and choices that were already available to us that made things just go very, very smoothly. So there's the Zealous Renderer, which already gives us the look and feel that we're used to with Scratch. Keyboard navigation, thank you so much. This is something we've wanted for a very long time in our Blocks code spaces, and we get it out of the gate with this one. So I'm really happy about that. The Continuous Toolbox plugin was really nice for us because we already use this same look and feel for code blocks. So that gave us some consistency there. Plus minus, thank you. The general mutator input for Blockly is kind of hard particularly for younger users, and also in general, I found you always have to zoom in just to be able to hit it, particularly on a tablet. And so having a much larger hit target that's easier, great, I love it so much. And then shareable procedures. We knew we wanted to have procedures, and just having a plugin that gave us that right out of the gate was also really good. So here's our toolbox. I'm just going to go over this really quick. We've got our categories. We've got our control blocks, which are all of our event handlers and our branching statements and loops. Math and logic blocks. This was also very easy because, like I said, we've got 2 existing blocks editor spaces, both of which use math. So that was kind of a copy and paste so that we have exactly the same blocks. So here's where the kind of meat of our robotics comes in, is with our output and input. So these are all the things to set and adjust motors, and I want to point back to what you'd said earlier about this sensor being used as an actuator. We also realized that as our version 1 with just motors, we can also use our motors as inputs. So that's what that is, and then of course variables and procedures. So how does Blockly measure up? Really good. It was generally really easy to get started. The ease of defining blocks was really good, and headless code generation, which is very important for us because you're not always in that editor. Sometimes you've already built a component or robotics element that you just want to reuse, and you don't want to have to go revisit the code. And so just being able to generate your code on the fly is fantastic. There were some challenges along the way. The mutator and comment interface is just really not friendly enough for a younger audience, we thought. Several of the plugins that we used, I noticed, conflicted with each other. They would all come in with the assumption that there's no other plugins there, and they would often try to collide, and it would make the debug output very noisy. And then keyboard navigation conflicts with our own shortcuts, in particular one, which is that for the physics simulation space, we've already used the paradigm of play and pause, and typically that is tied to the space bar for most applications, as it is for ours, and that's already used by the keyboard navigation as synonymous for enter. So enter and space are tied together, so I had to do a little bit of work to kind of uncouple that, so we wouldn't confuse the 90% of our users that are already really used to using spacebar to start and stop physics simulation. So we had to develop our own extensions. Hopefully this video will load, but I'll just start talking about them now. So for orphaned blocks, we apply this styling so that it's really, you can see that it's not going to do anything and it won't compile into your final code. We added a filtered field dropdown. This allows you to have a stale value still show up in your field. So it's something you can't pick now, but it still shows you where you came from. Keyboard, field dropdown keyboard that allowed us to use the keyboard, the React-based keyboard control that we're already using as a dropdown. And then the expand collapse and inline comments or in-block comments, because we wanted, again, to avoid the existing comment and right-click to collapse and expand. We thought were kind of hard to access, so this made it a little bit closer to what we wanted. Great. So now demos. Hopefully this loads. Otherwise, I'm going to have to talk about. Okay, so these are things I came up with while developing this. So here's a line following robot. There's a small hump that it's following with 2 ball switches. And whenever one gets lifted, it knows to turn. Here is a maze-solving robot that looks a little bit like a Roomba that just uses some switches on the edge, and I sped it up here so we don't have to wait for the 1.5 it takes for it to navigate the maze, but it just follows the left-hand wall to find its way out. Inverted pendulum, so balancing a stick, which is a classic physics example. And this one is one where we're using a motor as an input as well. This is a ball sorter that is, as it's picking up the balls, it's measuring the size of the ball so it knows which bin to put it in. Also make note of those gears. Those are going to come up in a later talk. So overall, this worked beautifully. And this was just 4 months of work to get to where we are now. You are the first people, I think, outside of our team to actually see this, because this isn't released yet, the robotic space. This will be released towards the end of the month. I don't think I'll try and slip in Blockly version 13, but maybe shortly after release. So now, I guess, any questions?
Hi, Christopher, former Blockly team member at Google. I'm curious, the block set, you already had presumably a set of Scratch blocks in the other environments.
Yes.
For this one, when you were thinking about the blocks, were you trying to make them look as much as possible like the existing ones, or were there design reasons to make them different?
No, good question. So they do differ a little bit. Like, for example, with the plus-minus extension, we modified our, if then else, so that you can have those, because previously it was just if, and then if you want another one, you have to kind of chain them, and you end up with this really large nested thing, and it's very ugly. But for the most part, we did keep them about the same. If you look at the circuit space, the categories, they match 1 for 1.